Professor Narasimha, Professor Chandru, and my many friends here. I see Professor Vishwanathan. I'm very happy to be here on this occasion, largely because, although I must admit I'm not a computer scientist, I have, however, been very interested in computing, and have always had people working with me who helped us along on whatever we wanted to do. And a lot of it had to do with fluid dynamics. But there were some other things as well. First of all, I must congratulate the department, CSA, on this occasion. It's a golden jubilee. It's a long history now. And my memory goes back to the old days when, I don't know, Professor Rajaraman is here. The late Professor I.G. Sharma, I worked with them. You mentioned parallel computing. So one of the persons I went to at that time was Professor Rajaraman. And I remember working with Professor I.G. Sharma when a satellite launch vehicle called the ASLV, Augmented Satellite Launch Vehicle, crashed twice, exactly the same way. So, although after the first one, they thought that solved the problem. The problem had not been solved. So it was actually a very interesting thing to work with. And Professor Sharma made a big contribution to figuring out exactly what had happened. And that's, of course, another story in itself. And there were several other people. So I'm happy. I wish the department even greater success as the days pass by. I'm sorry, did something drop here? Oops. Okay, yeah, I think hold this for a second.
This thing's always tricky.
Yeah. Thank you. Yeah. So I wish the department a great future and an even greater future. And I'm very happy to be here on this occasion. Well, I begin with positivism. I have a fair number of slides. I won't go through each one of them in detail, take time. But it's there so that if anybody asks questions or wants to see it in greater detail, the details are there. Well, a very simple definition of positivism is that it's any system of knowledge that relies data on data of experience, actual hard data, so to speak, and rejects metaphysical speculation. And what sort of speculation? I'll come to that in a short time. So there may be many different kinds of positivism, and there are, I'll mention some of them later on. But the one that became very well known was what's called logical positivism. Somewhere in the late 19th century to the mid-20th century, the philosophy took hold of the imagination of scientists and of analysts, and I suppose in some sense of philosophers too, in Europe. There was the famous Vienna Circle, for example. So, in more precise language, all knowledge must be based on positive data, that's where the word positive comes from, of experience. Beyond facts, you use only logic or pure mathematics, nothing else. Theology, metaphysics, and so on had to be relegated as irrelevant. Animistic, anthropomorphic explanations ruled out. Pascal's ultimate reality shunned. In other words, it's just facts and logic or mathematics, nothing else. Now, it attracted a lot of attention, many followers, but also many critics. And in the 20th century, it involved many very important people. All of these were involved in the in that argument. Einstein, you all know, Mach, from Mach number, same man, Karl Popper, went on. Hilbert spaces, Gödel's theorem on logic. So all of these played a big role, and there were many arguments about it. And there were people who defended it very seriously, and others who tried to find problems with it. Well, I can't help telling you about this little story about what happened at that time. That was around the time when the atom and molecule were being discussed a great deal. But while the idea was circulating, real evidence for it hadn't been shown yet. So, well, the atom then doesn't qualify from the standards of the people who follow logical positivism. The physicists, however, had gone ahead and, based on a variety of reasons, they'd gone ahead and written theories and ideas about atoms and molecules, even when they had not actually seen it or had hard evidence for it. Boltzmann, for example, wrote his famous book on the kinetic theory of gases, all the molecules, but he was criticized, saying, "What are you talking about molecules? Who knows about them? Have you seen them?" It was so bad that Boltzmann actually committed suicide a year after these charges were made against him. Funnily enough, a year later, a French scientist, Perrin, observed, could give solid proof that there were molecules. Brownian motion was one thing which was actually demonstrated it. So, so it's had a history of its own. But after that, I think things changed a little bit. Okay, now that's the famous positivism that we had. Now, I want to spend a little time talking about the nature of Indic scientific thinking, and I'll take astronomy as an example. It's a very good example because they're made to make lots of calculations to predict positions of planets and so on. How do they actually do it? Now, the methods used in India were very different from the methods used in Greece, and I'll show you where they differ. The first text on astronomy in India was the first one. By the first I mean not the first book, but the first one which lasted 1,000 years, and set a line of thinking for the rest to follow. If you look at the Aryabhatiya, and I compare it with a Greek book in a short while, it starts with an invocation to Brahma. For the first thought in your mind is, well, you just said God should not come in. How come God comes in? I come back to that. But it's only an invocation. It's not appealed to on any fact or result. It's full of numbers. Starts with the method of writing numbers with his own code. Revolution numbers. Kalpa, Manu, these big long ages. Planetary orbits, Earth's rotation. The fast and slow epicycles, Manda and Shikra. Science, how do you calculate science? So it's full of things of this sort as it starts in the first introduction. Well, here there is a sine table, believe it or not, in old Kannada script. I just put it here because I knew that it was there and wanted to get a copy. Here it is in Sanskrit. Here it is in the Kannada script. And here it is in Sanskrit. And right down there, I've written down what it reads like. Bucky, 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 and so on. It doesn't look like a sine table, but it is. It's a very clever system for producing 4-digit numbers in syllables, short syllables, half syllables, and so on. Well, the results on the signs here are correct to 4 decimal places. And it goes from 0 to 90 degrees. He knows that that's enough. And therefore, in some sense, was ahead of the card tables that were used in place of the sign in Greece. So, and it actually lists only differences, making interpolation easy. It actually, it's very clever. It had to be very, very compact because you had to mug it up. On the whole, it sounds very clear, playful, terse, deep, unfussy, business-like. But all these other operations are also there. Ganita, and it goes through all of this, squaring, cubing, how do you get square roots, cube roots, etc., etc. We don't want to go into that detail, and derivation of the differences. Sums of series, rule of three, so on. Kala Kriya, the reckoning of time, the celestial sphere. And it's a total of some 50 odd algorithms. What is it? It's actually basically a set of algorithms in the other chapters. But the interesting thing is that while he's making these algorithms, he quite often makes a side comment on something very physical. For example, eclipses. And of course, there is the shadow. He believed in the shadow theory. And as the shadow passes over the moon, as the earth crosses the sun, it's circular, so the earth is a globe. And then people will ask, why do people not fall off? Because it's gravity, the earth holds them by gravity. And so. But it's made as a side comment. It's never made as something of a fundamental piece of physics. And so it's from one point of view also very interesting. Reckoning of time, the celestial sphere, and so on. Now, I come back to Aryabhata in a short while. But I want to go 1,000 years later. There was an astronomer and mathematician in Kerala named Neelakanta, the last one of a very famous Kerala school. And at the end of a result, he makes this statement. Etat sarvam, in Sanskrit, etat sarvam yukti moolam eva, natu agama moolam. That's to say, all of this, all of what he has done in that book, is rooted in yukti. That's to say, human effort, human intelligence, human cleverness. Not in the agamas, not the scripture. It's nothing to do with the scriptures. He wants to make sure. And at another place, he similarly makes sure there's nothing to do with God. So, you see, you can see now what the resemblances are with positivism as it came in Europe in the 19th century. Well, the Siddhantas that they got that way were not always universal in time, and as Professor Chandru mentioned, they kept on correcting it. They said once in 100 years, you should check that once again and maybe fiddle with the numbers, so then it will keep quiet. And then a new Siddhanta must be created. And he also says, if there's a slightly new Siddhanta, shouldn't be ridiculed, shouldn't be punished. So it's actually for progress. Well, here are another couple of sentences from him about all that is known. Okay. Avidita sarvasya. Pariksha can you do not. Pariksha is examination, observation, data. See. Pariksha can you do knowledge. And that knowledge comes from inference. Anumanena. Anumana in Kannada is usually suspicion. But Anumana in Sanskrit is actually inference. It's inferring something from a result you have. And it's been followed by many Indian mathematicians all the time. Now, suppose you compare it with the Greeks. The famous book among the Greeks is Ptolemy's Almagest. Almagest is actually Arabic. This book 1 is totally different from chapter 1 in Aryabhatiya. Totally. It's another world. He has many hypotheses and assumptions to make. You can look at them as a list of axioms that were necessary for him to make these astronomical predictions. But at the same time, the physical model he has in mind for those axioms to be used. Things like this. I'll give you an example. Geometrical model started with perfect circular orbits, then circles and circles leading to epicycles. Then asymmetry was introduced. The planet was stuck to unseen revolving spherical shells of transparent crystal. Why? You can see the planets. So, well, if you believed in vacuum, you say it's all vacuum, so we see it there, or the air is very thin. But they didn't believe in vacuum. Who was it? I think Aristotle was it who said nature abhors vacuum. And so it's going around, but at different speeds, so it was stuck on crystal. And there were several spaces. So you can see, it's actually a very complicated physical model, mostly from aesthetic considerations, as the Greeks like to appreciate it. Okay, so that's where it was. Now, There was a comet in 1577, and it cut across the nested spheres I talked about, and which was inconceivable. And so slowly the interest in it was lost, and around the same time, Kepler's orbits also had been discovered, Copernicus, and therefore the model was abandoned. When you compare it with Aryabhatiya, it does not start with arguments and hypotheses at all, but it starts with some initial conditions, which I list there. It's all computed with some initial condition 4.32 million years ago. And so very specific data are given. Planetary motions decomposed to mean and rapid, with corresponding epicycles, which actually we most probably borrowed from the Greeks. On the other hand, used it in a totally different way, not the way that the Greeks were using it at all. Half ellipses and even curves, which are not differentiable at a point. Sorry. You see, for example, one on the second, a patched ellipse, they said, was also something which you could use to get the results right. Well, I should go back here. And a favorite phrase with them is Druk Ganitaikya. Come back to it again. Druk is seeing, observation, perception. Ganita is mathematics, calculation. They should be the same. And if the two are the same, then it led to Siddhanta. This is the principle. This equation is the principle. Now, this thing carried on for thousands of years, and late in the 18th century, 1790, this is just to tell you how accurate these calculations were. This is written in 1790, 100 years after Newton's famous book and his laws. And it's written by John Playfair, and he is dumbfounded, he's puzzled. He's at one and the same time totally puzzled and also dumbfounded. He says, how is it that the Indians have results in their almanac which are much nearer to the truth than Ptolemy was? His agreement with Lagrange is only a very recent scientist there, is remarkable. How is it that observations made in India when all Europe was barbarous or uninhabited, you see, he admits to those, made in Europe 5,000 years afterwards, how is it that they come in mutual support? How is it that there is exact agreement with the conclusion of Monsieur de Laplace? He is just totally dumbfounded. So he has various ideas about it. Maybe that when he makes these comparisons, he says maybe that was accident, but no. He takes 9 parameters. It's not an accident. All 9 parameters agree very well. And maybe in the old days, there was a Newton among the Brahmins under Lagrange. See, they're very recent people. And maybe that's the only way that they could have done it. Yeah. Wonderful, therefore, that some ages ago there had arisen a Newton among the Brahmins. And how does the Brahmin? Well, you see, this was largely the work of Brahmins at that time. So his article is also called The Astronomy of the Brahmins. He obtains his results with wonderful certainty and precision. The rules still more artificial and ingenious, extremely simple, so nearly exact, extraordinary. Okay, but after having said all of that, he said, they follow its rules without understanding its principles. They give no theory and satisfies itself with calculations. So that was the other side of what the Indians were doing that he saw. Well, so our buzzwords and their buzzwords were very different. I won't go through this axiom, proof, and so on in Greece, but in India, Prayojana, Anumana, Ganita, Druk Ganita, and so on, Siddhanta, and so on. Very different. Now, there's, I think, a widespread misunderstanding in India about the connections with God. As I told you already, most of these books made sure that nothing was attributed to God. although they may mention God, but that was not for using in the processes. And if you look at Bijaganita, Bhagavas Bijaganita, he first has something to praise in terms of that Avyakta and so on. He's playing a pun here. One, which is a prayer to God, but the other one in praise of algebra, in praise of Bijaganita. And then there was also this extraordinary school called Sankhya. Sankhya's thoughts are actually worth looking at. They were in a peculiar way very rational, not committed to the idea of God. And right there you see, na vastu siddhi. You can't make anything material come out of nothing. Although there are still people who will tell you here how they can do it and make demonstrations of it. There's Occam's razor in Europe, but there was Kapila's razor here earlier. Nothing to be done except for an additional principle, inappropriate, imagine, unnecessary entities. Now, the next one is what I want to see. Ishvara Siddhe. You ask him, do you believe in God? The reply is, we have no evidence. We can't demonstrate God, so we don't want to talk about it. Now, this is one of the oldest schools of philosophy in India, and still among the 6 orthodox philosophies till today, Sankhya. So the fact of whether a God existed or not depended on your belief, and it did not make you a non-Hindu. So that's one thing which I want everybody to understand. Well, here's another one. Aryabhatta, towards the end of the book, he says this is what he has done. From the ocean of the real and the unreal, I've dredged some gems of knowledge. These gems of knowledge I've talked about. Sailing the boat of my own mind is very particular. Sailing the boat of my own mind. In other words, I did that. It's really my work, which has, however, has been the gift of God. God gave me the mind, but nothing else, and everything else is what I've done myself. And that's was misinterpreted. 1,000 years later, we have this recorded. Must have happened many times. In that same Neelakanta, we go back to him, and one of his students comes and says, well, there is God there. Why do you say that it should be there? And he says, Manda, dull-wit, fool. He says, Aryabhatta doesn't mean, by the invocation of Brahman, that he is using, but Brahma has helped him and made these calculations. Aryabhatta himself did it. Okay, now I say all of that because that's what positivism is about. And because Indians may find it hard to believe that if you say you didn't get anything from God, or it's all God's gift or something, then it would not be positivism. But in many of these cases, when the results were actually involved there, they were very clear that it was not from God. Went out of the way to make that clear. Okay, that's computational positivism. Now, well, I think that I can skip these. Computational positivism make any sense? It worked for about 1,400 years between Ptolemy and Newton. And it avoided the excesses of the unjustified axiomatizations and proofs of late Greek science. Francis Bacon was a scathing critic of the Greeks. For him, the Greeks were useless. The Greeks actually spoiled the whole business. And he says, words and words, he says. and he has no great respect for what the Greeks had done. Why? Because in the 1,000 years following, for example, the end of creative period in the Greek civilization, nothing had happened in Europe. Those were the Dark Ages. Those 1,400 years were the Dark Ages in Europe. Nothing had happened. And Bacon sees that the East is doing very well. And he says there's something very wrong. And what is wrong? We've been following the Greeks. That's what he says. Okay. Let's see, you must tell me when I should stop. 5 minutes. 5 minutes? 5 minutes, okay. I just wanted to say there can be different ways of doing science. There's a Greek way, there may be an Indian way. And that had a pleasant argument between Feynman and Dirac. Feynman used to say there are 2 ways of doing physics. the Greek from principles and axioms, and the Babylonian, relating one thing to another. The Babylonian is rather like the Indian. So he says, I am a Babylonian. I am not a Greek. So he wants to make sure. I have no preconception about what nature is ought to be, or what it's like. Now he's talking here with Dirac. On the left is Dirac, on the right is Feynman. That's on the campus of Caltech. And Dirac is exactly the opposite. He says it's more important to have beauty in one's equations than to have them agree with experiment. You see, it's just the opposite. This is the opposite of what we call positivism. You say you start with facts, but he says no. What is important is that there should be beauty in equations. So he was in fact therefore going even one step beyond the Greeks in about beauty and aesthetics and so on. But he also admitted that his equations were smarter than him. But Feynman was just the opposite. He said, worship the phenomenon, not the explanation. I don't tell nature what to do. She tells me, he said. A very great deal more truth can become known rather than can be proven. So he was also distancing himself from the Greek view. Well, I think he was a very interesting person. I don't want to go through in that in detail. So there are actually continue to be different ways. The Greek and for some time the Western. Of course, there are still many Western scientists who think of the Greeks as the greatest scientists, the place where science started. And there is something to it. Of course, during its heyday, Greece was actually doing many things. But you don't very often hear about the wrong conclusions they came to, just because of the weaknesses that we have talked about. Now, computer technology is what's changed in the world now. You can now do calculations very fast, big ones, and it is beginning to influence the epistemology of science, I think. The precise thing I'll discuss in a little while. Is it returning with a bang? Well, from one point of view, it's surprising that it's similar to what mathematicians were doing. But from another point of view, it is not quite as surprising as you might think. Here is a very honest assessment of what has happened in the world, what happened in the world in mathematics. This is made by Hubbard Boyle, a very well-known mathematician. Wrote a book on quantum mechanics, widely studied and read. He said Occidental mathematics in past centuries have broken away from the Greek view and followed a course which seems to have originated in India and was transmitted with additions to us by the Arabs. And what is the big difference between the Greek view and the Indian view? The big difference is that in India, the number appears as logically prior to geometry. Whereas in Greece, geometry was the first. The numbers took second place. In Greece, number took first place and geometry came later on. So today, big data is the news all over the world. As I told you, I'm not a computer scientist, and I'm sure I don't have to say these things to you. You will know much better than me. Computer technology has now reached the stage where huge quantities of data can be processed within a manageable time. I think a revolution has started taking place. I believe that there was a similar but much smaller revolution some 1,500 years ago when the Indian numeral system spread across to Europe first and then all over the world. It changed our idea of mathematics. Before that, mathematics meant Euclid. After that, mathematics meant equations. Now we can now make a case that the revolution of modern science that began some 4 centuries ago was in part triggered by the new computational power of the numeral system, and by the techniques of algebra and the language of equations that accompany it. So, such developments do have the power to change epistemologies. Big data might do this because its huge sample size will give reliable correlations. long before the causal links may be worked out. That is roughly what Indic astronomy did long ago, but we are now doing it with very high technology. Artificial intelligence, machine learning, and so on are now becoming power tools as high performance computing moves towards the exascale. So, it may be no surprise if high technology makes computational positivism return to the world of science. Thank you very much.